Hi there, welcome to a Q&A episode of Space Nuts. I'm Andrew Dunkley and it's good to have your company as always. We've got a lot of questions today. We've got three. We might squeeze in an extra one, time permitting. We'll just leave that one hanging in the ether for the moment. But what would be the effect on dark matter if something big exploded like, a star? That's a question that has come into us. Ryan wants to talk about the sun's ecliptic. What does that mean? I have no idea. But we'll answer the question anyway by making something up. And we've got a question from James about planetary rings. That's all coming up on this Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Yes, I feel good. He feels good. We all feel good. How do you feel, Fred?
Oh, I feel terrible. No, feel good too.
Excellent.
It's a feel-good show, is Space Nuts, so you can't really do anything else, can you?
Well, the Q&A edition tends to go that way. We get all sorts. We even get genuine questions sometimes, which is always nice.
From our listeners, that's right.
Shall we just go straight for it?
I think we should. I think that's a really good idea and very
big
timely.
hesitation. I was a bit worried there for a minute.
Yeah.
But we'll go to our first question. This comes from Damien on the Gold Coast. We're not talking about West Africa. We're talking about southeast Queensland because there's a Gold Coast in both places. In regard to dark matter, if there's 5 times the amount of it to ordinary matter when Betelgeuse explodes, will the explosion blow away the dark matter as well? Would this now make the neutron star 1/5 of the mass until the dark matter returned? That's from Damien on the Gold Coast. Interesting question. We don't know much about dark matter, but could it or would it be affected by something as dramatic as Betelgeuse or some other star exploding supernova style?
No.
That's interesting. Because I thought the answer would be yes.
Yeah, I thought you might think that. Yeah, and it's no. And that's because dark matter does not interact with normal matter at all, except by gravitation. So an explosion blowing things away needs a physical push. It's usually a shock wave that passes through a medium. And yes, if dark matter responded, that shock wave would compress the dark matter. You'd have all kinds of phenomena. But dark matter doesn't interact with normal matter. And so it ignores the explosion completely.
Wow.
And we know this because of observations that have been made. And I think there's at least 2 examples of this, Andrew, where you've got clusters of galaxies which are colliding. Now, you can use clusters of galaxies to basically reveal where dark matter is in them, because you can look at the way the space around them is distorted by gravity, and the dark matter contributes to that. And the way you investigate that distortion of space is by looking at distant galaxies beyond. You can look at their shapes and the extent to which they're twisted or their images are twisted, and figure out how much the space in front of them is being distorted, and that distortion comes from the matter of the galaxy clusters. So to come back to the point, as I said, there's at least a couple of examples of this where you've got 2 galaxy clusters that have collided and basically ground to a halt. Their hydrogen gas that accompanies galaxy clusters has sort of compressed itself and is excited enough to emit radiation in the X-rays. But you can sense where the dark matter clouds that originally accompanied these galaxy clusters have gone. And it turns out that they just carry on going without batting an eyelid. So what you've got is basically a cluster which is formed of 2 clusters coming into collision. And on either side of it, you've got the dark matter clouds that were associated with the original galaxy clusters, which have just carried on going as though nothing had happened. And so that's an extraordinary example that illustrates very cogently that we don't see any interaction between normal matter and dark matter.
Oh, okay. I'm surprised. I thought the two potential answers were yes or we don't know. But
There's no.
It's no.
Yeah, it's pretty well no, and it's because that's if there was a reaction, if something did happen, that would be great because we'd be able to detect the dark matter and have a much better idea of what it is than we have now. So, Damien, your question's a good one, but has perhaps a surprising answer.
Okay. Very interesting. All right. Thanks, Damien. Let's move on to our next question, which comes from Ryan.
Hey, guys. It's Ryan here from Townsend, Delaware, voted Delaware's third most okayest town. I had a quick question for you. I was thinking about how the sun revolves or orbits around our galaxy, and granted it takes, millions, hundreds of millions of years to make a trip around. But I was wondering about our ecliptic in regards to how the sun is moving around the galaxy. Are we orbiting the sun like a hula hoop around a dancer as they go around? Are we orbiting more like a halo around the sun as we move around? What is our orientation of the ecliptic as it pertains to the sun's orbit around our galaxy? Thanks a lot, guys. Keep up the great work.
Thank you, Ryan, and I hope you're enjoying being number 3 most okay town. I can tell you with absolute certainty that Dubbo wouldn't rate in the top 3 of anything in this country. We cop a lot of stick from the media, probably because of the name of our town, but it's very unfair and they're all wrong. But it's good to be number 3. Now, I might get you to explain, Fred, just to sort of get our heads around it. How does the sun's orbit work on a galactic level?
Yeah, it's a great question, and it's got a great answer as well, which is 62 degrees, 36 minutes.
Oh, okay.
So that's the angle that the sun's path around the galaxy, around the center of the galaxy, that's the angle it makes with the equator of the Earth. So let me just step back a bit, because that, the end of Ryan's question was, what's the orientation? And that's the answer, 62 degrees, 36 minutes. But we don't call it the ecliptic for the galaxy. So remembering that the ecliptic, as seen from the Earth, is the path of the sun through the sky. And it's tilted with respect to the equator, and that means that the Earth's axis of rotation is not perpendicular to the plane of its orbit. It's not standing upright in its orbit. It's tilted at 23.5 degrees. So that's the ecliptic, as we call it, and it's the apparent path of the sun through the sky. Of course, it's the Earth actually moving around the sun, but that's what we see. Now, in a similar fashion, we can think about the path of the galactic center through the sky as the solar system moves around the center of our galaxy. The difficulty with this is that it takes 200 million years to go around once. Yep. And so you don't see it every year like you do with the ecliptic. You see the sun going around every year. But we do know that the sun's path is fairly near what we call the plane of the Milky Way galaxy, basically the disk, the plane in which the disk of the galaxy lies. The sun's path is fairly close to that. It may wobble a little bit up and down as it goes around the galactic center. There may be disturbances caused by giant molecular clouds and things like that as it passes. But we know from the observations of the stars around us that those are not particularly high-level disturbances. The thing is really going around mostly along the galactic plane. And so what that means is that you can define the angle that makes with the equator of the Earth, and it's what I said, 62 degrees 36 minutes. So the Milky Way is tilted over at quite a high angle compared with the ecliptic, which is tilted over at quite a small angle, 23.5 degrees. And in a way, if you imagine the way the Earth is, the sun and its family of planets, as they progress around their path around the center of the galaxy, they're not lying in the same plane as that path. They're sort of tilted upwards to it at quite a steep angle, and so that's how the sun and its planets move around the center of the galaxy. It's not, as Ryan conjectured, it's not sort of moving around the halo of the galaxy or anything like that. It is sitting firmly in the plane. It's just an ordinary star in the main part of the Milky Way.
And it's doing what billions of other stars are doing, and our planets are doing what billions upon billions of planets are doing throughout the galaxy. And it's just going around and around. Yeah, so it's a slow motion dance that's happening fast. More or less.
That's right. Or it's a fast motion dance that's happening slowly, whichever way you want to put it.
Could be both.
Yeah.
It's all relative. Okay, thank you, Ryan.
This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, we've got a question from James. Shalom, gents, he says. I've got a question regarding planets with rings. Could there be a planet with multiple sets of rings that are different to each other? I'm envisioning something like rings wrapping around an equator from gravity as per usual, but some other materials possibly being caught in the north to south magnetic field at a larger, smaller diameter than the equatorial rings. Thanks for entertaining my nonsense, James Greenfield. It's not nonsense. It's a question and it deserves an answer, James. We're going to tackle that one right now. Most rings, like the ones around Saturn, which are the most prominent in our solar system, are made up of dust and rocks and ice and bits and bobs. So what else could they be made of, Fred?
Well, yes. So it would be debris of some sort or another, gas, dust. I think James's question is.
I know, the rings around Earth, which are made of metal.
Yeah, that's right. They are.
And paint.
And they go around the equator as well, like the rings of Saturn, and like the rings of Uranus and Jupiter and Neptune. So I think James's question is, could there be rings that go at a different angle from the equator of a planet? And the answer is probably no, because this debris tends to be squashed down into a disk. In the case of Saturn, it is mostly icy debris, bit of rock in it as well, but mostly ice. And it's squashed down just by gravitational forces in connection with the rotation of the planet. So it tends to be forced into the equator of the planet. So a ring that's tilted at some jaunty angle, a little bit like what we've just been talking about with the disk of the galaxy, that is, I think, highly unlikely to happen. Even if you envisage it being entrapped with magnetic fields and things of that sort, I think we'd be struggling to make a ring that would not be at the equator of a planetary body.
Okay, so no on both counts. It's probably not going to ever be made of anything else, and it's probably not going to move beyond the equatorial.
Yeah, that's right.
Rotation.
Yeah, equatorial plane.
Plane, that's the word I wanted.
That's the word.
Couldn't think of it. So, yeah, sorry, James. Good idea, but not likely. Now, have we got time for one more? I reckon we could squeeze one more in, Fred.
Yes, it's yes, we can be quick on this one.
Yeah, all right. Let's be quick on this one. hello and best wishes to you both. A couple of questions about solar activity. One, what are the differences between solar flares and coronal mass ejections? Two, what predisposes red dwarf stars to the outbursts of solar activity that would seem to challenge development of life on planets in their solar systems? Thank you for the answers, and thanks for very much for a terrific podcast. You guys are stars. Boom. Mark from Bloomington, Indiana. Question one, what's the difference between solar flares and coronal mass ejections, Fred?
So it's mostly a matter of degree, but I think the physical processes are different. A solar flare is something that is generated by magnetic activity. It tends to come from sunspot regions when there's a high level of magnetic activity there, and we think of the magnetic field lines stretching between sunspots, which come in pairs, and one has a northern polarity and one has a southern magnetic polarity. So when they are particularly energetic, then you get solar flares. I think I'm right in saying that coronal mass ejections start off the same way, but if you get these magnetic field lines breaking so that there is a kind of magnetic twang, what you get is mass actually being expelled outwards at a great velocity. It's almost like an elastic band breaking on a gigantic scale, and that gives you a significant ejection of material, a significant ejection of the subatomic particles, which are there all the time in the solar wind, but with a mass ejection, you're getting a very much enhanced level of these subatomic particles being ejected from the sun.
And that's the thing that worries people around the world in terms of the interference with electronics and,
exactly,
of course,
yes,
the beautiful aurorae that we see in the north and south of the planet. There's some pros and cons to coronal mass ejections, but with reliance on electronics, that's becoming an area of concern. Well, it's not becoming; it is an area of concern if we get hit directly by something super nasty like that, Fred.
Yes, that's correct. So the second part of Mark's question
red dwarfs
is a good one. And he's right that red dwarfs are much more active on this sort of scale. We know that they are more, the outbursts of subatomic particles are much more prevalent. And I think, thinking back to my studies of stellar evolution and things of that sort, these stars have star spots on them, which are huge. They are very large compared with the star itself. And I think that might be one of the reasons why you've got much more activity, because they have enormous star spots on them. And in fact, I was just talking only today to a couple of my colleagues who are the experts on exactly that in this country, at the University of Southern Queensland. Brad Carter and Stephen Marsden, they did research on this, and I've worked with them in the past on it. They can actually map where these star spots are on stars. They do it with a technique called Zeeman Doppler imaging, which is a fairly esoteric technique, but allows you to make maps of the surface of stars. And their red dwarfs have got very big star spots, which I'm sure is why you get big solar flares. Now, Mark's next question, if he was able to talk to us, will be, why do they have such big star spots?
Yes.
And the answer to that is, well, I'll go and ask my colleagues because I don't know the answer to that. But it's clearly something in the evolution.
That bloke you were talking about, Zeeman Doppler, he might know.
That's two blokes, actually. Herr Doppler and, it would be Herr as well. Zeeman was Dutch. So there you go.
All right. So it's probably the big spots that are causing red dwarfs to be so nasty. So they're planets where it's very difficult to establish life by the sound of it. We've talked about that before, but that's probably what prompted the question from Mark.
I'm sure it is. It's a good question too, Mark. Thank you.
Yes, it is. Thank you, Mark. Thank you to everyone who contributed. Don't forget to send your questions in to us via our website, spacenutspodcast.com, spacenuts.io. Click on the AMA link at the top. It's right next to About and Support, which you can also do. And you can send text and audio questions there, or send us the audio questions from the Send Us Your Questions button on the right-hand side. As long as you've got a device with a microphone, you are set. And don't forget to tell us who you are and where you're from and what your town's ranking is. We really want to know that in terms of livability. Tell us something about where you live. We'd love to find out. It's always good to know. And don't forget to follow us on social media and subscribe on YouTube. I've been reliably informed that we only need 9.4 million more followers to get paid $1 a year. Woo!
There you go.
Big money in social media. Yeah. Thank you, Fred. We are done again.
It sounds great, and great to talk to you as always, Andrew. And I look forward to the next time.
Indeed. Catch you soon. Fred Watson, astronomer at large, and thanks to Hugh in the studio, who wasn't in the studio today, but thanks anyway. And from me, Andrew Dunkley, thanks for your company. We'll catch you next time on another edition of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.